Moving on to Module 14C, the speed of sound. No new vocabulary for this unit. So, there are 4 characteristics that describe a wave. We've already discussed these, and they are speed, wavelength, frequency, and amplitude. Experiment 14.2 in your text gives an illustration of how sound waves travel through air with a certain speed and how to estimate the speed. I recommend that you stop the video right now and read that experiment and then come back. In the experiment, the average of a typical pace is measured. So a pace is the distance between your feet when you walk. A helper takes 2 rocks and paces until the helper and the observer are about 250 meters or 250 paces apart. The helper strikes the rocks together. The observer actually sees the rocks striking together before hearing the rocks striking. This is because we see light before we hear the strike of the rocks. This also happens because light travels at a faster speed than sound. In the experiment, a stopwatch is then used to mark the difference in time between seeing the rocks strike together and hearing them strike. The experiment is repeated 9 more times and the result is averaged. The averaged result is then divided by 250 meters. The answer is the speed of sound. The speed of sound in air is given by the following equation. In the equation, V stands for the speed of sound. The capital T stands for temperature, which is always measured in degrees Celsius. So, we have our formula, and it says V equals 331.5 plus 0.6 times T. Now, once again, let's look at this. The T stands for the temperature, so this would be the outside temperature where we're doing the experiment. And that temperature can change the actual results for the speed of sound. So let's work through example 14.2. If the temperature is 68 degrees Fahrenheit, which is 20 degrees Celsius, what is the speed of sound? So we substitute 20 in our equation. And the first thing we have to do, remembering your PEMDAS, is multiply first. So we'll multiply 0.6 times 20, which is 12, and then we will add our results together. We have 331.5 plus 12 becomes 343.5 meters per second. So in this situation, the speed of sound would be 343.5 meters per second. Now let's look at another example. A physicist is watching a thunderstorm. She sees a flash of lightning and then hears a thunderclap 2 seconds later. If the air temperature is a cool 15 degrees Celsius, how far away was the lightning formed? Now this is just the first part of what we need to find. First, we're going to find the speed. So we take our formula and we substitute the 15 degrees Celsius into the formula. We now multiply the 15 by 0.6, which gives us a result of 9. And we add the 9 to 331.5. Our result for the speed will be 340.5 meters per second. Now that we found the speed, what we need to do is find the distance that the sound traveled. And let's return to a previous formula that we've used way back, I think, in Module 9. Speed equals distance traveled divided by time traveled. But for this application, we're going to use algebra and basically twist this formula around a little bit. So we'll have distance traveled equals speed times time traveled. So what we did was we multiplied both sides by time traveled, and we no longer have a fraction here. The distance traveled we just solved for, and the distance was 340.5 meters per second. And how long did it travel? Well, let's go back to our original problem. And there it is. She heard a thunderclap 2 seconds later. So we'll substitute 2 seconds right here for the time traveled, and 340.5 times 2 is 681 meters, and it's no longer meters per second because you can cross cancel the seconds out of the equation. Now that the speed and the distance have been found, there's another way to estimate these amounts. Because thunderstorms are usually the result of cold fronts, they're very cool. A good guess for the temperature would be about 16 degrees Celsius. At 16 degrees Celsius, sound travels about 341 meters per second, or about 1/5 of a mile per second. So, for every second of delay between the strike and the thunder, it's about 1/5 of a mile. If you count 2 seconds between a flash and thunder, the lightning struck about 2/5 of a mile away. If you count 5 seconds between the lightning strike and thunder, that means that the flash was actually 1 mile away. So that's what you can do. The next time that you see lightning, go ahead and start counting, and remember that about 5 seconds should be about a mile. If you need any help, please be sure to ask, and we'll be moving on to video 14D.